Okay, so our next speaker today is Taylor Hutchison, who's going to talk about near-infrared spectroscopy of galaxies during reionization.
All right. Sorry if you hear a train in the background. There's one going by. All right, hi y'all. I am Taylor Hutchison, and like they said, I'm going to be talking about near-infrared spectroscopy of galaxies during reionization. So we've had a lot of really good talks already, kind of motivating why we all care about this particular subfield of extragalactic astronomy, and in particular highlighting the usefulness of the Lyman-alpha mission line for probing the epoch of reionization. So to just kind of springboard from that and jump right in, Lyman-alpha is a really useful tool for looking at these galaxies in this epoch. However, there are some complications with it. It's a resonant line, it's subject to scattering, can be heavily attenuated by neutral hydrogen, and often the redshift you derive from the Lyman-alpha emission line can be hundreds of kilometers per second redward from where the true redshift actually is. So here's a beautiful example of this. This is a Lyman-alpha spectrum from Dan Stark's work in 2015. And you can see this asymmetric shape, and the blue dashed line is the redshift you derive for Lyman-alpha. Notice that it is offset from where the systemic redshift for the source would be, which is the red dashed line. And so obviously this kind of pushes that there's a need for a systemic tracer. And ideally, the criteria you'd want to meet is your systemic tracer should not be attenuated by neutral hydrogen or outflows, should represent the true redshift of the source, and ideally, be in the ultraviolet because we're working with galaxies in the epoch of reionization. So some of your best bets are going to be some of these red lines I'm pointing out. So carbon-4, PM2, O3, and carbon-3. However, your true best bet for the epoch of reionization is most likely carbon-3, as it's often the second brightest line in the UV after Lyman-alpha, and also is really ubiquitous in these high redshift galaxies. And so once you have a systemic redshift and a Lyman-alpha redshift, you can compare the two and come up with this measurement for the Lyman-alpha velocity offset, which is the equation on the bottom, which can give you insights into the kinematics of the galaxy and possibly whether or not there's neutral gas as systemic. All right, and additionally, with these UV metal lines, they're also powerful probes for stellar populations, the type of ionization and the strength of it that's in these galaxies, and then also the chemical enrichment that's happening in these galaxies. So to start off, there's a quote unquote pilot study that we did. So essentially the way the process worked is we took a galaxy at redshift greater than 7 with Lyman-alpha that was spectroscopically confirmed. From there, we do follow-up spectroscopy targeting the carbon-3 doublet, which is a 1907, 1909 angstroms, to try and find systemic redshift. If possible, if it's in the same wavelength region, we also would try and target the silicon-3 doublet. From there, we measure the systemic redshift compared to the Lyman-alpha redshift, and then adding in available photometry and any other ancillary data, compared to photoionization modeling to walk back for low metallicity, high ionization models, what kind of galaxy properties might best match our observed properties. So the galaxy we chose in particular is this one originally detected by Steve Finkelstein in 2013, Lyman-alpha redshift of 7.51. You can see a poster stamp of it on the bottom left. This galaxy has an IRAC color of 0.8 magnitudes, fairly red, but as you just saw in Guido's talk, this might not be unexpected. And so we did some follow-up spectroscopy in H-band with the Keck Mossfire spectrograph, and you can see the spectrum on the right-hand side. We definitely detected carbon-3, but as you might notice, it's a doublet, and we're actually only seeing one part of this doublet. Unfortunately, it's so perfectly placed between these two skylines that whichever part of the doublet it is, the other line falls behind one of these two skylines. So by eye, it makes it challenging to determine which part of the doublet we've actually seen, but through comparison of other measurements that we have and also work from the literature, we've determined that the line we most likely have is the 1907 part of the doublet. However, I'll also show you solutions for if it's the 1909 line. So from this detection, we can get a systemic redshift for the source of 7.5032, which yields a Lyman-alpha velocity offset of 88 kilometers per second, which is very small. This likely implies that there's hard ionizing radiation, it's systemic, that's likely clearing out some neutral hydrogen, allowing Lyman-alpha to escape closer to the systemic redshift. From assuming a line ratio of the two parts of the carbon-3 doublet, we can get a combined line flux, which then can provide us a rest frame carbon-3 equivalent width for the line. And this gives us, it's 16 angstroms, which is strong, but again, not really unexpected for these young, highly star-forming galaxies in this epoch. So from there, we compare with our photoionization modeling and any available photometry. So as we saw in Guido's talk, a really good tool you can leverage at redshift 7.5 is the fact that you have O3 and H beta popping up in the 4.5 band. In this case, we enjoy this possibility. And so for the 3.6 minus 4.5 IRAC color, what this means is there's nothing in the 3.6 band, so you can essentially see this color kind of as a proxy for the O3 and H beta equivalent width. This is what we're showing you on the x-axis. On the y-axis, we have the rest frame carbon-3 equivalent width. And so for each of these subpanels, you're seeing a range of different models where we're varying on the left-hand side, for instance, we're varying the color, which shows this change in stellar metallicity. The line type is this change in nebula metallicity. And then starting at the bottom left and going up to the top right, we have an increasing ionization parameter. And so what you're seeing on the left-hand side are the BPASS stellar population models with binary stars involved and an upper mass limit that extends to 300 solar masses. And you can see that there's pretty good agreement. It covers a lot of these different types of models seem to cover the space occupied by the dark red star, which is the preferred solution that the line is in 1907. The light star is if the line is 1909. On the right-hand side, you see stellar population models using starburst 99, where the IMF only extends up to 100 solar masses. And you can see that very few of the models seem to reach into the space occupied by our galaxy, at least within 1 sigma, so you're kind of seeing these two different extremes with these two different stellar population models, and kind of highlighting that the most likely matches for this galaxy are these low metallicity, high ionization galaxies that have really strong, that have possibly disconnected stellar metallicity and nebula metallicity. So additionally, I mentioned that we were looking at the silicon-3 doublet. It was actually not detected in our H-band spectrum, but that's actually fine because you can actually still get some really interesting information from non-detections. So we placed an upper limit on silicon-3, and then by taking a ratio of silicon-3 to carbon-3 and comparing it with our modeling by varying the ionization parameter, which is the x-axis on this plot, you can see that as the ionization parameter increases to the right, this ratio drops. And it also seems to be more heavily affected by metallicity towards the higher ionization. So what you can see here is even with the upper limit, where we don't actually have a detection of silicon-3, we still seem to find agreement that this modeling suggests that the galaxy most likely has this high ionization and low metallicity, which is in really good agreement with the separate measurement of the carbon-3 equivalent with IRAC color, which is really exciting. So there's some really useful information you can get from literally 1 detection and some upper limits. So the current work is kind of building off of this. So taking all of that information and the techniques that we use, but now extending it to do a broad sample of galaxies from the literature, from redshifts 5 to 8 that have Lyman-alpha measurements, spectroscopically confirmed. And of course, we'll also have a photometric sample as well. So there's also a priority sample from redshift 6.8 to 8, which I'll explain why it's priority in a second. But yeah, so it's work as usual. We're going to target these rest UV emission lines. Now we're extending to all of them, and then kind of follow the same procedure and try and pull out information, any information we can for these galaxies. Just as a note, a detection of more than one of these lines for a particular galaxy can provide significantly increased constraints on the possible stellar population properties for these galaxies. And like I showed you before, even non-detections can provide some really valuable information. So the current program, we are using Keck MOSFIRE to target these rest UV and nebula emission lines in galaxies from 5 to 8. The priority sample is actually really exciting. So I realized that with MOSFIRE, there's this sweet spot in redshift where you can get from 6.8 to about 8, you can get some number of lines in the MOSFIRE J-band, and then some number of lines simultaneously in the MOSFIRE H-band. So for instance, what you're seeing in this plot here is a simulated stack of MOSFIRE data showing just some of the UV lines that we care about, and then overimposed are the MOSFIRE J and H bands that are de-redshifted, but showing what you see for redshift to 7. And so for redshift to 7, you could potentially get carbon-4, helium-2, and O3 in the J-band, and then simultaneously get silicon-3 and carbon-3 in the H-band. Now, it's important to note that a lot of these lines might be really faint, but still, even non-detections, like I pointed out before, can provide really interesting constraints. So for this program, we have been awarded 8 J-band nights in 2018 and 2019 for Rebecca Larson's work, PIing, targeting these Lyman-alpha emitters at redshift 9 and greater. This work was done as a secondary science case for that program, and so we were able to look at redshift 5 to 6 targets, targeting the carbon-3 and silicon-3 emission. And then we now have an additional 4 nights awarded in 2020 for this full J and H band program, which is really exciting. And so we have some exciting preliminary results, but also just as a shout out, Rebecca Larson's done an amazing job with the data reduction process and analysis. And so you should definitely keep an eye out for her upcoming work on that. So to kind of show you a few preliminary results, on the left-hand side, I'm showing you just a cute serendipitous O2 detection in one of our spectra. This is, this is what we wish we could see at this redshift. But this is showing you a very beautiful doublet detection and also the unique signature of the MOSFIRE data because of the dithering technique we use. And so you'll have a positive trace in the middle and then a negative trace above and below. This is real things will have this trace. So just to show you a handful of some of the tentative detections of UV lines at redshift greater than 5 that we have, here's just showing you a handful of them. I'm being coy and not telling you what they are or the redshifts that they have because I want you to stay tuned. We'll be showing you them in the future. So this is all preliminary work as a note, but it's really exciting. We're already getting some results, and hopefully we'll be able to get these analyses done and these answers to you as quickly as we can. But just kind of as a plug, Guido already showed it, which was wonderful. But James Webb, you know, we kind of have to talk about how amazing it is. At least I feel like I need to. It's going to revolutionize what we do, as we know, but I'm just particularly excited about the implications for the nebular physics you can do with it. And so, for instance, as he showed, this is a thing I ran through the ETC. This is just showing some of the models that best matched the Galaxy from 2019. And you can see that with 2 hours on the prism, with a resolution of about 100, you can get from Lyman-alpha all the way out to optical 03. And now, of course, some of the lines are blended, but even some of these detections can just open the door for this playground of nebular physics. And it's just really exciting. So I hope, you know, knock on wood, that goes up soon. And so, yeah, so I'll leave up my summary slide and I'll take questions. Thank you.
Thank you for that, Taylor. So just waiting. Doesn't appear to be any questions at the moment, which is a new one. Oh, sorry, my computer was just taking a while to update. So we have a question here from Rebecca Bowler. Could you explain more about how the sample was selected? Could it be that very strong line emitters be excluded by these criterion?
That's a good question. So for now, the sample is just chosen from photometric sources that from photometry and with SED fitting that seem to match the redshift range we care about. We're not getting specific on trying to do selections by estimated stellar mass or anything. And then the main sample are from sources that have been spectroscopically confirmed for Lyman-alpha. So there obviously is a bias here. They have to be spectroscopically confirmed via Lyman-alpha. So this tells you a lot about what the galaxy might be like. So we're definitely not going to be using this as a indication for galaxies as a whole, these redshifts. But yeah, that's mostly where the samples are coming from.
Okay, great. Another question here from Michaela Bagley. This is quite a long question, so hopefully I'm going to read it out properly. If you allow the stellar IMF to go up to 300 solar masses, then the metal yield ratio of silicon to carbon is supersolar, which is already expected at high redshift anyway because of the weak contribution from AGB stars at early times. Does the analysis of the silicon non-detection allow for non-solar abundance ratios?
That's a fantastic question. So for that particular work from 2019, we didn't actually explore anything past assuming solar ratios, but that is definitely work in the future with more lines. Ideally, I would like a detection of silicon-3 to really do that analysis. But yes, that's definitely the next step, is looking into the variations of abundances, including those kinds of relationships, yes.